Hey everyone, so in this lecture we will go through few more practice problems on stacks and queues. So this is practice problems part 2. So let's get started. Now let's see the next problem. It was asked in GATE CS 2016. It says you are given a circular queue with capacity of n-1 elements implemented with an array of n elements. So the strength of the array is n, but you have to implement a circular queue with capacity n-1. So this is what we also discussed in the circular queue. The only difference is they are taking rear and front pointers in the array. We have taken like tail and head respectively, and initially both are 0. Okay, so this is exactly the scenario that we discussed in the circular queues. So we need to detect the condition in which the queue is full and empty, overflow and underflow condition. So it's easy only. So in our case, we have like taken tail plus 1% n is equal to head. This is overflow, right? Why? Because if there are already n-1 elements, in that case, if you increase the tail by 1, in this case the tail is rear. If you increase the rear by 1 and take modulus of n, it will become equal to head or the front. So this is correct for the overflow state. And for underflow, initially for empty, initially it is 0. So you can also like see from the initial condition both are 0 and equal. So tail when it is equal to head, it's underflow or so it's just you replace tail with rear and head with front. So we've already like seen that it will always have at max n-1 element if the total capacity is n. So A is the right answer. Alright. Let's see the next one. Okay, so this was asked in GATE CS 07. So the problem is, suppose you are given an element of a queue of integers. So there is a queue and it has integers, and you are given an not element, it's implementation. The operations that can be performed on the queues are, so 3 operations can be performed, whether you can check whether it's empty or not, delete an element and insert element I in queue, right? And like the operations are like similar to what we can have in a queue, which is the insertion will be at rear and deletion will be from front. Okay, so a code snippet is given to you and you need to comment about what change this code will bring to the original queue, which already has like few elements. Okay, all right, so let's take an example. Let's assume the queue has 3 elements, 1, 2 and 3, because like the assumption is a queue is given with implementation of a queue of integers. So there are already some elements present in the queue. Let's suppose this is the queue. It has 1, 2 and 3 elements, right? Now you need to perform certain operations. We will trigger this void f with argument as the original queue or the queue that is given to us. Okay, and if you note it's a recursive function. It is first checking whether it is empty or not. If it is not empty, in that case it is deleting an element, then again calling f of q, and after this call is over, we are inserting that I back to the queue. Okay, so let's see. This is a very good example to understand how this queue and stack works. Why? Because there is recursion involved. This f is again called inside the same function. Okay, so let's make a call stack. Why? Because it's a recursive function, so we need to trace the recursion in order to get the answer. Okay, all right, and let's call it line number 1, 2, 3, 4 and 5. Okay, so for the first time when you trigger this function, when this is triggered, it will allocate a space on the top of this function stack. Okay, this is the first call with the queue having 3 elements. Okay, so initially this queue is 1, 2, 3 for which it's called, right? So now a local variable I is declared. So we have this queue with 1, 2, 3 as 3 elements, then we have I. But before putting the value in I, we are checking whether it's empty or not. In this case, it is not empty. Initially, it will have 3 elements, the assumption that we have taken for the reference. So now the line number 3, when we trigger line number 3, it will delete the element from the queue. It will delete, this is front and this is back, or rear or front, you can call it anything. Okay, so the first element that will be removed once the delete operation is triggered would be from front, right? So this will be removed and the value of I at line number 3 would be 1. This one is removed. Alright. Now at line number 4, again this function will be called. But we are passing a queue which do not have the first element. Why? Because we have already deleted an element from the front of the queue. Okay, so now again we are calling is f, but the queue would be only having 2 elements, 2 and 3. But before going to the next function call, we need to add the return address, which is line number 5 should resume once the next function call gets empty, or like gets completed, not empty. So it should return at line 5, correct? Okay, so now for the next function call, what will be the value of q? 2 and 3. Q will be 2 and 3. Q will be 2 and 3. Again we will check whether it's empty or not. The answer is no, it is not empty, having 2 elements. So delete will be called and it will remove 2, the next element which is present in the front. I would be 2 in this case, right? Can you see it? After you remove 1, front will be 2 and delete operation will remove this 2. Okay, and then again this f is triggered. At this time the queue will be having only 1 element, but we need to first add the return address, return at same line 5, correct? Now this f is called second time in this recursion with value of q as 3. Yes or no? And at this point, line number 2 will check whether the queue is empty or not. The answer is no, it is not empty. So again, this delete will trigger and now the front will be marked as 3 and this will be removed. This will be removed. 3 will be removed and value of I would be 3. Correct? Line number 4 will again trigger this function call with an empty queue. At this point, the value of q is the queue is empty, so it will trigger f, but the return address would be 5, return at line 5, but the final call would be with an empty queue, queue will be empty. So at line number 2, that there is a check, it is checking whether the queue is empty or not. The answer is yes, the queue is empty, so it will return, correct? It will return to line number 5. So now at line number 5, there is an insert operation in the queue and we are adding the element I of that specific function call. In this case, I is 3. So line number 5, what it is? It is insert q comma I in the queue which is empty. You are adding I. So the value of q will be, in an empty queue you are inserting I. The value of I is 3, the value of q is empty. So this insert operation will add I to q. Okay, so the value of q will be 3. This would be returned. It's over and it will return. Okay, at this point now we have this q, the value 3 will be there, and at line number 5 again this insertion would be there. I am adding I, which is 2, to the q. Okay, so the value of q will be 3 comma 2. The value of q would be 3 comma 2, and this will be over. Return back. At line number 5 I am adding I to the q. Right? So in this case, and the value of q is already 3 comma 2. It will be 3, 2 and 1, and it will be returned. Okay, so initially we started with q. We started with 1, 2 and 3. Initially, and finally we end up with 3, 2 and 1. Okay, so just check the options. So what operation is performed by the above function f? A is leaves the queue unchanged. Answer is no, the queue is changed. Reverse the order of the elements in the queue. Correct, it is reversing the order. C deletes the element at the front of the queue and insert it at the rear, keeping the other elements same. No, we are reversing the elements. Finally, D option empties the queue. No, the queue is not empty. So B would be the right answer. The elements of the queue will be reversed. Alright. Okay. Next problem. It was asked in CS 97 and it is also an interesting problem. So in the start of this lecture, we have seen an implementation of a stack using 2 queues. Okay, we all know it, how you can implement a stack using 2 queues. But in this problem, a priority queue is given. And what is asked? They are asking to implement a stack using a priority queue. Okay, that stores characters. Push C is implemented using insert. So push is the function that we have to implement using this insertion. This insert is the insert operation in that priority queue, in which you are trying to insert the character C to queue with key K. And we already know, like we have discussed in priority queues, that there will be a key associated with all insertions. Okay, either it will be a max priority or a min priority, where K is an appropriate integer key chosen by the implementation. So, and the second operation, pop, of this virtual data structure, which is a stack implemented using a priority queue, is implemented as delete min. So we can only use insert and delete min of the priority queue operation in order to implement push and pop of the stack, right? So for a sequence of operations, the keys chosen are in. So we need to comment on the order of the keys are, and 4 options are given: non-increasing, non-decreasing, strictly increasing or strictly decreasing. Okay, so let's have an assumption for all 4 options, and then we can easily figure it out which would be the most appropriate one, right? So in case of non-increasing order of keys, all these options are associated with keys. What should be the order of keys in order to perform push and pop using insert and delete min operations of the priority queue? Okay, so first one is non-increasing order. So let's have an example. Non-increasing order, what exactly a non-increasing order is? So the order of keys is either constant or it will decrease. Okay, so non-increasing order, it should not increase, it can remain same or it can decrease. Let's assume 3 is the key, first key, then 3, then 1. Is it the correct sequence? If I have to take 3 keys, let's assume for simplicity we are only having 3 keys, 3 insertions, 3 keys in non-increasing order. Is the sequence non-increasing? The first is 3. The next is 3. Is 3 greater than the previous 3? The answer is no. 1 is greater than 3? Answer is no. So it is a non-increasing sequence. It's correct. Okay. Similarly, take a non-decreasing order. What can be a non-decreasing order? A non-decreasing order is an order which should not decrease. Either it can remain same or it should increase. Either it should remain same, 1, 1. It is same, or it should increase, 1, 1, 3. Right? Okay. Third, strictly increasing. Every subsequent key should be greater than the previous one. We can take 1, 2, 3. And finally, for fourth, strictly decreasing. You can take any decreasing order. This is just for understanding or eliminate which are the incorrect options. So I have taken 4 sequence of keys, out of which we can easily check that 3 will get discarded based on the operations that we have provided, either delete min and using delete min and insertion to implement push and pop of the virtual stack that we need to implement using this priority queue, which can only store characters. Okay. So these are the sequence these are the keys that we'll be using. So let's see one by one. Let's check for the first one. For A part, let's check for A part. Okay. I want to perform 3 operations. Let's assume we are performing 3 push operations and then there is a pop. So we are implementing a stack. So it should always happen that the last pushed element should be the one to be removed first. Then only it will be a last in first out data structure or a stack. Okay. So let's fix, we are having 3 push and characters are push A, push B and push C. And then we'll perform pop. Okay. So after these consecutive pushes, the pop should always remove the last pushed element, which is C, right? So now for this push, it will depend on the keys that we are taking using the insert. Okay. For A part, this is the stack. Initially it will be empty. The first operation would be I need to push C, but I can only use this insert in this queue character C with key K, and the sequence which we are taking for A part are 3, 3 and 1. Okay. So what it will add, it will first insert A with key as 3. It will insert A with key as 3. Correct? Push A with key 3. Then the second B with 3. And the third with character C with key as 1. Correct? Till this point, is it clear? What we have done, we have inserted, we have performed, we need to push 3 elements in this stack. Okay. So we are triggering 3 insert operations with keys in such a way that they are in non-increasing order, just to check whether option A is correct or not. Right? So this will be the state of the priority queue after the 3 insertions, right? And this element, this is the last one that we have added in this. Okay. So the order in which the pop should remove the elements would be, first it should remove C, then B, then A, then only we can call it a stack. But the constraint is the pop should be implemented as delete min queue. Delete min, what it will do? It will remove the element with the lowest key, as the name is delete min. Delete the element with lowest key or least key, right? Okay, so now I want to perform pop. Then again, let's assume one more pop operation. We are performing 2 pops. The order in which the element should be removed are C, then B, then A. Correct? Okay. So now the first pop operation, what it will remove? It will remove delete. It will remove the element with the lowest key. Okay. Out of these 3, which element is having a least key? The key is 3. key is 3, key is 1. So it will first it will give me, it will return C comma 1. Is this correct? Yes, it is correct. It is correct. It is removing the element with the least key, and we are validating whether this is C or not, whether it is the last element that we have pushed in the stack or not. The answer is yes. So first pop operation is correct in this case. Let's see the next pop. Let's see the next pop. So what it will return? What will return? The idea is to perform delete min operation in the queue. You have two keys, element A with key 3, element B with key 3. Both the keys are same. So it will depend upon implementation to implementation that which element should be removed. And in a priority queue, if any two elements have the same priority, then it depends just on the implementation that which element should be removed first. So there can be an instance that rather than removing B, the algorithm can remove A, and delete min still holds. Why? Because both the keys are same. So it won't matter for the priority queue that which element it is returning. So in a scenario in which it returns A, then then it won't be a stack anymore. In a scenario in which it returns A and not B, it can. Why? Because both the keys are same. Out of these A, 3, B, 3, it can remove anything. So if it removes A, 3, it won't be a stack anymore. And it is a valid delete min operation. Correct? So therefore it is incorrect. It is ambiguous, not incorrect. It is not exactly what we want for this priority queue to behave in order to have a stack. Okay, let's see the next one. Non-decreasing order 1 1 3. Again same operations for B part. First I want to push A with key 1, A, 1, then B, 1, then C, 3. The first operation, the first pop, that internally uses delete min. What it will give? It will return the key. It will return the element with the lowest key. In this case, either it can be A, 1 or B, 1. Let's assume it's A, 1. It will return A, 1, which is incorrect. Why? Because the stack is expecting the last element that got added to this priority queue to be removed, which was C, 3. So this is incorrect. Again incorrect. Similarly, for C, the keys are 1, 2 and 3. For C, the keys are 1, 2 and 3. A, 1, B, 2 and C, 3. Right? So what the pop will remove or delete min? It will remove the key element with the lowest key. In this case it is A. So it will remove A. It will return A, 1, which is again incorrect. The stack is expecting the pop should return C, 3. So this is also incorrect. And if the keys are strictly in decreasing order, then the last key which got added would be always the one with the least key, and delete min should always remove this key. So D is the right answer, and you can see it with the example as well. For this case, the order would be A, 3, then B, 2, then C, 1. C was the last element got added, which is having the least key among all possible elements. Why? Because we are ensuring that the keys are chosen in strictly decreasing order. The first pop would return you C, 1, which was the element that added on the top of the stack, or the last one. This is correct. So D is the right answer, strictly decreasing. And a similar option, which is non-increasing order, is not correct. Why? Because of equal keys, there will be a tiebreaker, and it will depend upon implementation to implementation that which key your priority queue is choosing to get removed. Okay, so yeah, let me write it more clearly. It will give you C comma 1. All right, the next one. So it says consider the following statements. First in, first out types of computations are effectively supported by stacks. First in, first out. No, stack is first in, last out, or last in, first out. In fact, first in, first out are queues. So first is incorrect. Implementing list on, all right. So we haven't covered the linked list yet. It will be the next lecture. For now, you can ignore it. Third one, implementing queues on circular arrays is more efficient than implementing queues on a linear array without two indices. It is correct. It is correct. Why? Because implementing a queue on a circular array would be more efficient. Why? Because it can at max store n-1 elements, which is not the case when you are implementing a queue using a linear array and two pointers. It will waste the initial spaces after few insertions and few deletes. Okay, so the third one is correct. Last in, first out type of computations are effectively supported by queues. No, they are supported by stacks. They are supported by stack. Queues support first in, first out, or last in, last out. So, but like if you have a basic understanding of linked list, you can easily figure it out, the second statement as well. Implementing list on a linked list is more efficient than implementing a list on an array. For all basic list operations, insertions would be easier on linked list. Insertions would be easier on linked list and not on array. Array, you need to like shift all the elements, but insertions would be convenient, right? So yeah, this second one is also correct. So 2 and 3. Okay, but even if you only mark 3 as right answer, so the only two options having 3 are C and A, out of which C gets eliminated. Why? Because 4 is anyway incorrect, right? So even if you like do not know linked list, you can easily mark the correct answer. Okay, all right, next one. So it was recently asked, and the problem says consider a stack data structure into which we can push and pop records. So a stack is given to you with basic two operations, push and pop. Assume that each record pushed in the stack has a positive integer key and that all keys are distinct. Okay, all numbers are distinct that you are adding to the queue. We wish to augment the stack data structure with an constant time min operation. So we already have this push and pop. What the problem says, we want one more operation in this stack, which is called min, and it should be a constant time operation. It should be a constant time operation that returns a pointer to the record with the smallest key present in the stack. It should give me the pointer with the smallest key present in the stack. Okay, so say the stack has 10 different keys. It should always return me the pointer to the smallest key in constant time. In constant time, this is the important thing that is mentioned. Okay, and two constraints without deleting the corresponding records. So we do not have to shuffle the elements or delete anything from the stack. The second is without increasing the complexities of the standard stack operation. Both push and pop should also occur in constant time. Basically, all three operations should be constant time operations. Okay, so we do not have to touch the current push and pop. So which one or more of the following approaches can achieve it? Okay, so let's see it one by one. First is keep with every record in the stack a pointer. Okay, what it says, generally what we are storing in the stack is the elements. Okay, push 2, push 3, push 1, then pop, then push 4, like this. Okay, so option A is suggesting keep with every record in the stack a pointer to the record with the smallest key below it. Okay, so rather than storing just 2, store 2 comma some pointer which is pointing to the least element present in the stack below the 2. So whether it will resolve the whether it serves the purpose to give us a min operation in constant time, we'll see. Okay, so we need to like check it option by option and then figure it out which option or options are correct. Okay, starting with the first one. What it is trying to say, I have a stack. And I'm not only storing the elements in it. Along with elements, I also want to store some pointers. Okay, so let's have some addresses. Address of first block is 100, then it's 101, 102, 103, 104, 105. For simplicity, let's assume we have like the capacity of the stack is 5. Okay, so what first option says, I am storing numbers. It's fine. I am storing keys which like all keys are distinct, positive integers and distinct, right? All are positive and distinct. So along with the key, I am also storing a pointer to the record with the smallest key below it. Okay, so let's assume some elements. The order can be order can be 5, 7, 3, 9 and 10. Okay, so for the first push operation, it will store 5, and along with 5 we are changing the specific element which are getting stored in the stack. Earlier it was only numbers, but now it will be a number, data and pointer, correct? And what it will point to the lowest element below it. Okay, so for this instance, if I want to store the first, if I want to perform the first push operation, okay, initially the stack is empty, so what will be the value of this pointer for the first instance? Null, right? For the first element it will be null. Why? Because there is no element which is below the first element. That's why the pointer is pointing to null. Okay, now the next push, which is 7. The next push is 7. Along with 7, I also want a pointer which should point to the record with smallest key below it. Smallest key below 7. Since there is only there is an assumption, every element, the way in which we are pushing the elements, we are always ensuring that just the immediate top, before we have initiated the push operation, is always having a pointer which is pointing towards the least element below that, correct? So we can maintain a sequence in which you take any specific element. You can take any specific element, you will always get the pointer which will point to the lowest element below that. How? Give me a minute, we'll see. In this case, if I am pushing another element which is 7, okay, I will check whether the pointer which is on the top, which is of the top element, is pointing towards the least one, right? But since it's pointing to null, so there is no least. So the only least would be, we have to compare the value of this pointer and the exact value of the topmost element before putting the element. Okay, so what we'll do before pushing, so push 7, so we need to add 7 comma a PTR. So we need to somehow figure it out what will be the value of this pointer. Okay, so there would be two comparisons to get this value. Either it will be this pointer or it will be the immediate top of the element. So we need to take the minimum of these two. In order to get what element should this 7 point, correct? In this case, the top is pointing to null and the value is 5. So it will point to 100. Why? Because if I am at here and I need to check what is the least element present in the stack below it, it will be 5, correct? So therefore it will store 7 comma 100, right? So we have just tweaked the push operation in such a way that we have added 2 more comparisons before putting the element in order to find the value of this pointer. It will be more clear when we try to add the next sequence of elements in this stack. Okay, so 7 is done. Now it's time to add 3. Okay, again push 3. So the challenge is to find this PTR in constant time, right? Why? Because there is a constraint without increasing the complexity of the standard stack operation. So push is generally a constant time big O of 1 operation. We check the top and just add the element if there is no overflow. Okay, so this 3 is fine. We can add 3. Along with 3 we have to add a pointer. So what should be the value of this pointer, or which block it should point to ensure that it should always point the smallest element below it. Okay, so again 2 comparisons. We already know that before putting the element, before putting 3 on the top of the stack, there is 7, and the pointer is always pointing to the element which is smallest below 7, correct? So there are only 2 comparison in every push operation, which is I need to check whether this is, I need to compare the value which is present at this pointer and the subsequent top of the list, and whatever the least is, I will update the corresponding pointer with that value. That's it. Okay, all right. So for this pointer I need to compare that value at 100 and 7, whichever is least. In this case value at 100 is 5 and 7, so value at 100 is least, so I will store 100. I will store 100. In order to maintain this constraint that the pointer to the record should always point to the smallest element below it, so this 100 is pointing towards this, the least element. This is also pointing to the least, correct? So now next push will make things more clear. I need to add 9. I need to find the pointer. I need to push 9. And so 9 comma PTR. Again 2 comparisons. So I am not increasing the complexity of the push operation. Push is just check the top, give me the address where I need to add the element, and then 2 more comparisons in order to get the pointer. And if and like all these operations are constant time, so the push is constant time. Okay, so how we'll get this pointer? We will need to compare the value which is present at this address and 3, whichever is least will assign to this. In this case value present at address 100 is 5, so we will be comparing whether 5 and 3, whatever is smaller will get the address, will update the PTR to that address. The PTR should always point to either value present at address 100 if it is a smaller, or 3 if it is smaller. In this case will point to 3, so it will store address of 3, which is 102. It will store 102. So by ensuring that the complexity of the push is not increased, and at the same time the pointer to which each element is always pointing to the element of the least value below that, correct? So the subsequent pushes we can easily do. Let's have 10. So 10 and least is 102, so it will be 10 comma 102. So like this. Okay, so now the question is pushing in this way where the stack, every element of the stack is having a value and a pointer to the element which is the least below it. Okay, pushing in this way, is it giving me the minimum min operation in constant time? Okay, so if the answer is yes, then it's the correct answer, otherwise no. So let's check that. Okay, so I need to have this min at this instant. At this instant I have this 5, 7, 3, 9 and 10. Can I perform min operation in constant time? And by constant time I can't, I can only see the top. I can only see the top. So top is 100 comma 102. I can only see the top. So can I define the min operation like this? Okay, whatever the top is, check that. So s dot top it will be a value. A is s dot top dot val. Let's call it val and ptr, value and pointer. And B is s dot top dot ptr, s dot top dot ptr dot val, and return min of A and B. Is it a constant time operation? The answer is yes, it is. What I've done is I am seeing the top of the element, which is 10, and I am seeing the value of this pointer. This is the pointer which is always pointing to the least. In this case, it is 102. So I am just comparing 100, which is the topmost element, and the least present in this stack, and then just returning the minimum out of them. So it will always give me the min in constant time complexity. No matter when you call this, it will always give me the min. So A is right answer, and it is min is a constant time operation, and we have not changed the complexities of either push or pop. All three operations are constant time. Okay, so now let's check the remaining options. The second is keep a pointer to the record with the smallest key in the stack. Okay, so what option B is saying? Option B is saying let's keep a pointer. Let's keep one more variable called pt, which should always point to the smallest element in the stack. Okay, so in this example itself, so what will the value? The value will be 102. Okay, the pointer is pointing towards 3, right? And there are only the elements present in the stack are like this. The stack is like this: 5, then 7, 3, 9 and 10. Okay, I'm talking about option B. So PTR will, and the addresses are 100, 101, 102, 103 and 104, right? So PTR or PT is a pointer pointing towards the least value, and we can easily calculate by pushing. At the time of pushing the elements, we can maintain a variable called min address. So this min address should always point to the address of the minimum element. Okay, in this case 102 is fine. Okay, at this instance we can, in constant time, I can figure it out that minimum value is 102. Okay. But now what if I pop 10, 9 and 3? I popped 3 elements. Okay. At this point, this pointer is lost. Okay. The pointer is lost and it is not pointing to the minimum. In order to find the correct address that needs to be stored in this pointer, I need to traverse through all the remaining elements in the stack in order to get the new minimum. In this case, it is 5. So in order to update the pointer, so that it should always point to the least element present in the stack, I need to traverse if the specific address is popped out at any given instant. So therefore it is no longer a constant time operation. Min is no longer a constant time operation for B part. Is it clear? Is it clear? What I have said initially, somehow while putting the elements, while having the push operations, you have figured out that the minimum element is present at address 102. Okay, now what if that minimum is removed? What if that minimum is removed? Now in order to get the new minimum among the elements present in the stack, you need to traverse, and that traversal is not a constant time operation. So therefore B option is incorrect. Okay, third option, keep an auxiliary array in which the key values of the records in the stack are maintained in sorted order. Again, this is a problem. When you added this word that maintain it in sorted order, it can't be a constant time operation anymore. Sorting is itself a n log n operation, which is the best case. The best algorithm would take n log n time. So min won't be a constant time operation. Correct? Finally, keep a min heap in which the key values of the records in the stack are maintained. So the option D is saying maintain a min heap. We can maintain. The removal will be a constant time, but after removal. So we haven't covered the heaps yet, but the best algorithm to implement min heap, the deletion will be a constant time operation, but now we need to heapify. In order to maintain the heap property, we need to heapify that, and then that heapify operation will take log n time. It will be a big of log n operation. We'll see it in heaps, but yeah, the D option won't be a constant time. So the best is option A. Is it clear how maintaining the address in such a way that each push should compare with the element present at that address in the top of the stack and then decide which is minimum for the corresponding element that we are trying to push. Okay, in this way we can easily calculate the min operation in constant time. All right. Okay, so all right, that's all for this lecture. Hope you guys enjoyed it. We'll see you in the next class.